evening, everyone. In the previous live session, I discussed basic concepts about basic concepts and definition of thermodynamics. In that, I discussed the basic of significance of thermodynamics approach, and then after that I discussed the system type of system, open, closed, and isolated systems, and after that I discussed properties of the properties, and then two different types of properties like dynamic equilibrium. In that, three different thermal equilibriums, which are mechanical, chemical, and thermal equilibrium. And after that, we discussed quasi-static process and zeroth law of thermodynamics, and also the basis for temperature measurement and energy, sources of energy. I would like to energy transfer by work. I will start in just 1 minute, 1 minute break. I would like to see the YouTube. Okay. As it has already been defined, energy is capacity to do work. A closed system and its surroundings can interact in two ways, by heat transfer and by work transfer, and these bring about changes in the thermodynamic properties of the system. And thermodynamics deals with the study of these changes in the properties of the system. Transfer that takes place due to temperature difference between the system and surroundings is heat, whereas energy transfer that takes place other than temperature difference between the system and surroundings. More specifically, work is the energy transfer associated with force acting through a distance. In mechanics, action of force on a moving body is said to be work is said to be done there. The magnitude of the work is the product of force and the distance traveled in the direction of the force applied. A rising piston or rotating shaft and electric wire crossing the system boundaries are all associated with work. After that, to define the thermodynamics definition of work, thermodynamics work is the interaction between system and surroundings. In thermodynamics, that work transfer is observed at the boundaries of the system. It is defined as the sole effect on things external to the system can be reduced to the rising of a weight. Here, weight may not actually be raised, but the net effect on things external to the system is reduced to rising of weight. For that, let us take a battery and a motor fan arrangement. In this, there is a battery and a motor that constitutes a system, and system boundary is there. Here, battery supplies energy to motor. Motor will rotate the shaft that is attached by a fan. When energy is supplied to motor, that causes the rotation of the fan. Now, let us replace that fan by a pulley and weight arrangement. In this case, when energy is supplied to the motor, motor rotates that shaft, and in turn it rotates a pulley. That pulley will raise the weight. So the net effect on things external to the system is reducing to rise of weight. That is what exactly the definition of thermodynamics work. So a sign convention for this work transfer may be like this. Work done by the system, it is taken as positive. uh, that is work done to the surroundings is positive. For example, if you take the turbine, in turbine, uh, that high pressure steam enters the turbine, and it expands in the turbine and does work upon the turbine blades that will produce work, and low pressure steam comes out. Here work is done by the turbine. Here turbine is the system. So work done by this is taken as positive, and the system is taken as negative. In this case, W is negative. For example, if we take a compressor, in case of compressor, air enters the compressor at low pressure. Upon the application, upon the work on that application of that work on the fluid, that fluid gets compressed, and high pressure fluid or air comes out. Here work is done on the system, that is on the air. So here work is taken as negative. So these are the two sign conventions for the work done by the system or on the system. So if it is to be repeated, work done by the system is taken as positive, whereas work done on the system, it is taken as negative. The unit of work is Newton meter, or 1 Newton meter is nothing but 1 joule. If 1 joule of work is said to be done when 1 Newton force makes the object disturbed by 1 meter, is 1 joule. Of doing work, it is well known. Rate of doing work, either which is done by the system or on the system, it is known as power. Power has a unit joule per second, that is work per time. The unit for work is joule, work for unit for time is seconds, so it is joules per second. So if 1 joule of work is done in 1 second, then it is said to be 1 watt. Watt is the another unit for power. It is more popularly used. So if 1 watt power is either produced, work either done or on the system or by the system in 1 second, so that is 1 watt. After sign convention, let us discuss PD work. For that, let us select a piston and a cylinder arrangement. In this case, here the piston is initially at state point 1 with properties pressure P1 and volume V1. It is at thermodynamic equilibrium. Due to pressure, when the piston moves out, and when it is stopped at position 2, and then once again it reaches thermodynamic equilibrium, and its thermodynamic properties are pressure P2 and V2, and if it is plotted on a PV diagram, this can be seen like this. And now at any point intermediate between and final state point, its pressure is then once again it is at thermodynamic equilibrium, as thermodynamic properties are significant. Let us assume there will be a very small infinitesimal and the force applied on the piston like this, that force applied on the piston is given by pressure into area. So this is the pressure force that is applied on the piston when it is moving point. If there is an infinitesimal distance movement of the piston, then the infinitesimal work done is given by force into infinitesimal distance traveled, that is F into dl. Once again, the work is force into distance traveled. Here infinitesimal distance traveled is there. So in the place of this force, I am substituting B P into A into dl. In the place of F, I have substituted pressure into area. Here A is area of the piston, and dl is the infinitesimal distance traveled by the piston at any intermediate state of the change of state of this work or process. Here area into length is volume. So area into infinitesimal distance traveled is infinitesimal displacement volume dV. So this is pressure into dV, P into dV. So it is the infinitesimal work done when the piston moved by an infinitesimal distance dl. So upon integration, we will get integration from 1 to 2 P into infinitesimal displacement volume. So this is PTV work. This is the basis to measure work in any type of processes. So after that, let us discuss different forms of work. In that, the first form is electrical work. Here I am considering resistance as a system. Here current flows through resistance. As current will run the motor, in turn it rotates the shaft that will does work. So here work transfer takes place across the system boundary. So here we can define current as dc divided by d tau. Here dc is the charge that crosses the system boundary. In time d tau, there will be an potential difference of E. Then the infinitesimal work done is given by E into dc. Here E is a potential difference. It is equivalent to force definition of work, and then dc is the charge that is crossing the system boundary. Then once again, in the place of dc, I am substituting that is here. So that can be written as W, that work done can be written as integration from 1 to 2 EI into d tau to calculate the total work done. If we integrate from initial to final state, the product of E into I into d tau, we can get the total work involved. And after, the other form of work is shaft work. Here let us consider a shaft that is run by a motor. Here let us consider that shaft itself as a system, and that boundary is also given here. If T is the torque that is supplied, and N is the number of then when there is application of torque on the piston, there will be angular displacement. Then that is given by that work done in case of shaft is given by integration from 1 to 2 into T into d theta. Here T is torque that is applied, and d theta is the angular displacement that is taken place when the torque is applied. So this is how the shaft work can be measured, and usually the shaft work is if it is done per time, we will have a power that is usually mentioned with T into omega. Here omega is angle of the angular velocity. That power can be calculated. Always shaft work or the power that is developed by the shaft is very, very important in the daily usage of energy or work. Almost all works are supplied by this shaft work only, that is widely used in IC engines, in steam power plants, etc., etc. And after that, for that, I have selected a cylinder which is insulated through this cylinder wall. A paddle wheel is inserted, and this paddle wheel is driven by pulley and weight arrangement. Uh, Here, since the volume is fixed, the PdV work done by the system or on the system is zero. There will not be any PdV work in this case, but there is definitely work transfer, that is infinitesimal work transfer to the system can be either calculated with the amount of weight that is fallen down, or so here mgz is the potential energy, or that is work that is supplied when the weight is fallen, and that is converted into kinetic energy, and that is supplied. Or this can also be measured work. It is the product of torque that is applied and angular displacement that takes place when that energy is supplied. So this is the paddle wheel work, and after that the total work transfer in this case is given by W is integration from 1 to 2 mg into dz, that is equal to integration from 1 to 2 t into d theta. So this is about paddle wheel work, and after that we will have work that is produced by flow of fluid. Here let us consider a control volume. Here M1 is the mass flow rate at inlet, and M2 is the mass flow rate at exit. Here P1, V1 are properties of the fluid at inlet, and then it has a pipe area of A1, and then at exit the fluid properties are P2, the pipe is A2. Now here this flow work can be calculated in this way. Delta W flow is given by P into dV. Here then delta W flow can be written as P into V into dm. Here dV is V into dm, as the small v is a specific volume. So V small v, that specific volume small v, is dV divided by dm. So dV is V into dm. So after that the flow work at inlet is given by delta W flow in is equal to P1 V1 dm1, and at exit it is given by P2 V2 and dm2. It is the product of pressure, specific volume, and mass flow rate at exit. So this is about flow work. These are the important forms of work that we have more popularly seen. And after this let us discuss what exactly mean by free expansion. For that, let us consider a system. It is completely a system, and this is the boundary, and this system is insulated, and this system is divided by this partition, and one part is filled by gas, and the other one is vacuum. Now the when the partition is removed, what happens? uh, the gas rushes and fills the vacuum here, vacuum. uh, so in this case, work transfer across the system boundary is zero, but there will be PDV work, that is here PDV work is not equal to zero. Here expansion is taking place. There will be definitely change in volume, increase in volume of the gas. So PDV work is not equal to zero. There is some PDV work. So here expansion of the work against vacuum is called as free expansion. Then this free expansion work can be measured by having knowing the intermediate equilibrium points. That expansion of work can be measured when we know the path that is followed in changing the state from initial to final state. That is about a free expansion. Then let us discuss energy transfer by heat. As I told you, energy that is transferred across the system boundary by virtue of temperature difference is known as heat. Uh, the direction of heat transfer is always from a higher temperature to a lower temperature system. Usually this heat transfer takes place from a body at higher temperature to a body at a lower temperature, or from a region of higher temperature to a region of lower temperature within the body. There are mainly three modes of heat transfer, which are conduction, convection, and radiation heat transfer. In case of conduction heat transfer, more energetic particles of a substance transfer their energy to less energetic neighbor. Here energy transfer takes place either by lattice vibration or by movement of free electron. In case of convection, when the fluid flows over a surface that is at different temperature than itself, heat transfer takes place. The direction of heat transfer depends on the relative magnitude of the temperature of the surface and fluid. If the temperature of the surface is higher than the temperature of the fluid, heat transfer takes place from surface to fluid and vice versa. In case of radiation, it is excitation of the particles. In case of radiation, energy transfer first takes place to the surface, and it is emitted from the surface. And that is about the three modes of heat transfer. And the sign convention for this heat transfer, it is heat that is supplied to the system is positive. For example, where heat is supplied to the steam plant, that is working substance water in the boiler, where heat addition, it is taken as positive, and the other heat rejected by the system is taken as negative. Once again, in case of steam power plant, in the condenser, heat is rejected to the surroundings, that is taken as negative. Sign convention in case of heat transfer. And after that, and difference between heat and work. Here both heat and work are boundary phenomenon. They are observed only at the boundaries of the system, both heat and work. Both heat and work are path functions and inexact differentials. As I already told you in the previous live session, the magnitude of work involved depends on the path that is followed, as the area under the curve is the measure of the work involved in change of state from initial to final. So it is completely depend on the path that is traversed. Like that, heat also, the magnitude of heat involved in change of state from state point 1 to state point 2 depends on the path that is followed, as the magnitude of heat transferred is different as it follows the different paths. So both heat and work are path functions, and since they are path functions, they are inexact differentials. After that, let us discuss adiabatic process. A process in which no heat interaction takes place between the system and surroundings is an adiabatic process. It is a process when this process is plotted on the pressure volume coordinates. Then heat interaction in this case is zero. Usually the compression and expansion of in the IC engine are considered as adiabatic compression, adiabatic expansion in case of Carnot cycle. So that means there will not be any heat interaction during those processes. That is what process mean by. And after this adiabatic process, let us discuss about something about gas, that is equation of state. Properties pressure, volume, and temperature is the functional relationship between the properties pressure, which may be expressed in the form f of pbt equal to two of these properties are known, either pv or vt or pt are known. Then the third property can be evaluated from a hypothetical gas at all temperatures and pressure is called an ideal gas. It is very well known. The equation of state for an ideal gas is given by PV equal to mRT, where m is mass of gas. So be written as PV, where n is the number of moles of gas, and then points the equation of state is given by P1 V1 divided by T1 divided by T2. So for two state points, the equation of state can be written in this way. That is P1 V1 divided by T1 equal to P2 V2 divided by T2. Then let us know specific gas constant. For that, let us have equation of state for an ideal gas. As already told, it is given by PV equal to mRT, where m is mass of the gas, and R is specific gas constant, and then P is pressure, V is volume, and T is temperature of the gas at particular state. And then this specific gas constant, that is gas constant per unit mass, is given by this value, that is 287 joules per kg Kelvin for specific gas constant value for a gas, that is it is measured per kg, per unit mass of the gas. And then after specific gas constant, let us know constant. Here once again let's have equation of state for an ideal gas, that is given by PV equal to nRT. It is also on the molar basis, whereas for specific gas constant we took on the mass basis. Here we are taking on the basis of number of moles of gas. Once again, P, V and T are same as the previous one, such as pressure, volume and temperature respectively. Here R with bar symbol above is different compared to the specific gas constant. Here this universal gas constant is 314 joules per mole Kelvin, but whereas the previous one was joules per kg Kelvin, here it is joules per mole Kelvin. So this is the universal gas constant. So these are all the some in the first chapter, and after that this let us discuss a few important problems on a temperature scale. So for that let me take this problem. Here temperature T on a certain Celsius thermometric scale is given by means of a property through a relation T equal to A ln P plus B, where are constants, and P is property of fluid. If at ice and steam points the values of P are found to be 4 and 20 respectively, what will be the temperature reading corresponding to a reading of P equal to 60? So as I already told in the previous live session, to measure the temperature we will consider a reference body, and we will take some property that will change with temperature, and change with temperature of the property in temperature. That is what exactly I told. For this here we have the relation between temperature and the thermometric property. It is given by like this, that is T equal to A ln P plus